In this video, I'm going to look at an example problem that solves a force method analysis using an internal redundant for an indeterminate truss. So this truss system here that I've shown is externally statically determinate. There's only 3 reactions, so we can find all of the reactions using only equilibrium. However, this structure is also internally indeterminate, so I couldn't solve all of the members in this truss using only equilibrium. I could only solve the reactions. So that means I can't use an external reaction as my redundant force if I want to solve this indeterminate system using the force method. Instead, I'll have to choose an internal redundant. And for a truss, the internal redundants that we can select are the forces in the individual truss members. So this is a kind of odd-looking truss, and we're asked to determine all the member forces and reactions. And we have some external forces at the top at point D. So the first thing that we're going to do is to select an appropriate redundant. And so we can choose any of these members that we wish as long as the resulting structure is stable and determinate. But I'm going to select member BC here. So what we're going to do is we're going to cut member BC such that it can't take any axial force. We're not going to remove it altogether because when we reapply that redundant, we want to be able to take into account the deformations of the rest of member BC on either side of the cut. So we're going to get a primary structure that is determinate, and it's going to look like this. So here I've taken member BC, I've made a cut. For convenience, I'll call the ends at the cut B prime and C prime. And here you can see that member BC still exists so that the cut pieces can still deform, as I said earlier. So our compatibility criterion here is that for our real indeterminate system, the 2 ends of this cut have to be coincident. So when we apply our external loads, these cut ends are going to move. They might overlap or they might separate apart. And when we apply the redundant load, which is the axial load at the cut here, then these 2 points could overlap or spread apart. And our compatibility criterion then for the force method analysis is that those 2 deformations, one caused by the external force and one caused by the redundant at the cut, have to be such that at the end these 2 points C prime and B prime are at the exact same spot, so that the 2 ends of the cut member form together. So as I said, let's look at that compatibility condition, which is, as I said, that points B prime and C prime have to be located at the same point, because in reality, in our real indeterminate system, we don't have a cut member, we have a continuous member, so all of the points have to come together and there can't be a real gap in the system. And even for our primary system, when we have made this cut, so we just make a cut at any point along BC, as long as we don't add any loads to this system, then we're assuming that those cut pieces are actually formed together. So they won't separate until we add some either external load or we add a redundant load at the cut. So then our compatibility equation is going to be delta BC BC, which is the relative displacement of B prime and C prime under external load, okay, plus FBC BC, which is a flexibility, times the actual load that's in the member BC in our indeterminate system. So this one here is the relative displacement of B prime and C prime under the redundant unit load. So this is a flexibility. And that's because we're applying a unit load, so we're seeing how much are B prime and C prime going to overlap or pull apart based on a single unit load. And then so if we want to find out how much it is for the full load, we multiply that flexibility times the load. And FBC, as I said, is the axial load in member BC. Okay, so now just like in all of our other force method analyses, we're going to do two different analyses. One is to find this delta BC, and the other one is to find this flexibility FBC. And for this first one, we are going to use the primary system, which is a determinate system with the redundant force removed, or with the redundant restraint removed, and we're going to apply the external loads, then see how those two ends overlap. And then for the flexibility, we're going to again use the primary system, but now we're going to apply unit loads to both ends of the cut, and then we're going to see how much they overlap, and that will be our flexibility. So for the first part, finding delta BC, we're going to, as I said, use the primary system. We're going to apply that external load, and then we're going to find delta BC by using the method of virtual work. So our real system is the primary system, which looks like. So here it is, our primary system. This member is cut, so it can't take any load unless I apply load there. And then I'm applying my external loads, and I have my reactions. So I can find my reactions easily using equilibrium. That was 100. This one's 20 kilonewtons. And this one is 60 kilonewtons. And then I can go ahead and find all of the loads in my truss using the method of joints. So this one is 50.0, which is tension. This is zero force member. This is zero force member. This is negative 111.8 in compression. And this one here is 22.4 in tension. And you can try this for yourself and make sure that you can find all these forces by doing things in the correct order. You know, here I probably would have started here. This 20 can be projected into this direction to get the 22.4. And then down here, same thing for this one, for BY. Then the horizontal of the diagonal here can go to T. And then these zero force members come out. Obviously, I haven't included the dimensions on this drawing, but they are in the original, which is 5 meters, 5 meters, 5 meters, 5 meters. So now that we've found the real system for our virtual work, we can find the virtual system. So now, since for our virtual system we want to find the relative movement of B prime and C prime due to these external loads, do they overlap, do they pull apart, by how much, we're going to have to apply virtual unit loads at each end at B prime and C prime. So that's going to look like this. So here's our primary system. Here is our cut. I've separated it just for clarity, and we apply 1.0 to B prime and 1.0 to C prime, and this represents the axial force that's in that member. So if we look at this more closely, okay, then we're going to see we start with a system that looks like this. Again, I separated them in the overall drawing just for clarity, but in reality, we start with a situation where B prime and C prime, so this is a blow up here, B prime and C prime are in alignment here, so these are together. I can draw this to line right up. Okay, and now I've separated them obviously in this direction, but they are in alignment. And I apply 1.0 here and 1.0 here, and then after the deformation, we get some sort of overlap that looks something like this. Okay, so we have this overlap here, which in our real system is the delta BC. Okay, so we're applying the real forces, and we're trying to find the deformation. So the unit loads look like this, and this is after a real deformation. It's going to overlap like this, and we're interested in finding out how much this overlap is, delta BC, which is what our virtual work is going to tell us. So now, of course, this member actually exists, and our redundant is not the entire member. Our redundant is only the force at the cut in the member. So that member BC still exists. So we have to include the deformation of the rest of BC. So if we look at applying this unit load at the cut and the fact that this member remains in the structure and that we have to account for the deformation of it, then the situation above here, where we add the unit load at the cut, is equivalent to just adding a tension load to member BC. So we can just put a tension load here, and this would be equivalent to the situation that's up here. And it just makes it a little bit easier to visualize when we're doing our truss analysis, which is our next step. So which is to find all of the forces due to the applied unit tension, this unit tension, in member BC. So we want to find all of the forces in this truss now. So I'm going to redraw the truss and redo a truss analysis. So I'm going to start with this. There are no external reaction loads because there are no external loads applied. So I'm just going to look at this in terms of the internal truss loads, C and D. And so now starting with this one, I can find this force here, okay, which is negative 0.790. I won't go over the details of how to do this, and you can check out the truss analysis example the truss example video in order to find out how to do this if you don't already know. So then I can find this one from the horizontal components of these two. Then from here, I can find member AD, so the horizontal component of DB has to equal the horizontal component of AD. So this one is going to be in compression also, negative 0.790 in compression. Then I can find DC, which has to pull down, and this is 1.413 tension, and that just leaves this last one here, which is going to be 1.0 in tension. Okay, and now from here we have determined, so this is our virtual system. And from here recall how to do virtual work for a truss. Okay, if you remember, our virtual work equation is going to be 1.0 kilonewtons. Okay, so this is our external virtual force times delta BC, which is our external real deformation. And you can go back to virtual work in order to recall these. Then we have the sum of FV, which is our internal virtual force, which is what we just solved for, times FL over EA, and these are all together, right? And this is our real internal deformations. Okay, so these ones we get from our external load. Okay, these are the F, the L is the length of the members, EA are given, but in this case we're just going to leave them in terms of EA. And FV are our internal virtual forces, which are what we just solved for, and that's for each member. So for each member we're going to multiply the internal virtual forces times the real internal deformations, and that will give us our internal virtual work. So this is our external virtual work, if you recall, equals internal virtual work. Okay, so now we're going to use a table to do this. So let me fill out most of it. So I've just started with all of the different parameters that we have to determine and calculate. These are each one of the members. There are 6 members in this structure. These are the lengths of each of those members. Then I'm going to copy the forces in each of the members. Tension is going to be positive, compression is going to be negative, and that gives me these values. Then I'm going to go up to my external load calculations, which is this primary system here with the external loads, and that gives me F, which are the real forces, and that looks like this. Okay, and then so I have FV, I have F, I have the L, okay, which is different for each member. Now EA for this problem is the same for every member. So I'm going to just leave that out and put it in at the end. So what I need here is FV times F times L, not FVL, but I'm going to just take the numerator of this whole sum, FV times F times L. That's going to be just these three values multiplied together. So I'll fill out that column. Okay, and then so the EA can come on the outside of the sum since it's the same for every member. But so I can find the sum of FVFL, which is just the sum of all these values. So this is sum FV F times L, and that's going to equal 612.6. So then our delta BC, if we arrange this equation, which is our virtual work equation, we get 612.6 divided by EA. Remember EA I left on the outside. So that's delta BC, which is the first part of our compatibility condition for this force method truss analysis with an internal redundant. So the next step is to find this relative displacement due to the redundant load, which is a flexibility term. Now the good news is that the flexibility term reuses the same analyses that we've done previously. So to find this flexibility, we're looking at how do the ends B prime, C prime move relative to each other when we apply the redundant force at the location where we've released the redundant restraint. So we've cut member BC previously, so that is releasing the redundant restraint, and then we apply a redundant load at that interface, which is a 1.0 unit load in tension on B prime and C prime at the cut. So we apply the unit tension. Okay, and then we can notice that after we apply that unit tension, that this system, which is the primary system with the redundant, is the same as the virtual system that we used for the external load, which was where we added a unit load at that redundant location. So both of these are adding a unit load at the redundant location. So basically the systems are identical. So this system, we started with this, all right, which was applying a unit load for the purposes of doing the virtual work calculation, is the same as when we apply a unit load at the redundant location for the purposes of finding the relative deformation of B prime, C prime at the cut. So to restate that, we want to find the relative displacement of B prime and C prime, so the displacement of the two ends relative to each other, due to the above redundant unit loads that we're applying. So we're going to apply these loads and see how B prime and C prime move. The rest of member BC is still there because remember we're just making a cut at one point. And this relative displacement due to the unit load is the flexibility FBC-BC, which is in units of displacement over force. Delta over P, for example. So then if we want to find that relative displacement and we want to use virtual work, then we're going to have a virtual system to find FBC, BC. And that's going to look like this. So you remember for virtual work, when we want to find a certain displacement, we apply a virtual unit load at the location and in the direction of the displacement that we want to find. So here we want to find the overlap displacement of B prime, C prime. So we add a virtual unit load on either side of the interface. And this again happens to be the same as the virtual system for the external load, which was up here, right here. So for both the real system and the virtual system, for determining the effect of the redundant, we find that we're using the same system as we did for the virtual system for when we wanted to find the effect of the external load. So this is very convenient because it saves us a lot of work. So we don't have to do any more truss analysis from here on. We've already done the appropriate truss analysis. So this is the same as the virtual system for the external load and the same as the real system for the redundant load, which is this one here. So they're all the same. So this is going to make things very easy. So for finding the redundant for the effect of the redundant, right, the F forces, which are the forces in the real system due to the redundant, are equal to the FV forces, which are the forces in the virtual system due to the unit load at the location and in the direction of the displacement that we want to find. So therefore, our virtual work for this system is going to look like this. So we have 1.0 kilonewton again, which is our unit load. We have our FBC BC, which is the flexibility, which is actually the displacement that we're trying to find. Right, so this is our real external deformation. It's going to be equal to FV squared times L over EA. So FV and F are identical, and F equals FV, so F times FV is the same as FV squared. So we already found all those forces, and they're actually already listed in this table up here. So the smart thing to do would be to just add another column to this table that was, instead of FV FL, it's FV squared L. Now I'm going to just separate it and do it below, and I'll repeat it in the effort of completion. So if I fill these out, these columns here are the same as the previous table. So again, might have been not worth it to recopy these. Would it be just better to tack on an extra column, especially knowing ahead of time that we're going to need this in all of these redundant force and these force method analyses. We always run into this situation where the redundant system recopies the virtual work analysis from the external force system. So it's always a good idea then to just tack this onto the end of the previous analysis. So if we knew that ahead of time, which in the future we will, right, then we don't have to recopy this table all the time. So I'm going to now find the sum of FV squared L, so that's just the numerator here. EA are constant, so I'm going to leave them out of it. And we get 39.33 divided by EA. So again, we could have just included this column in the previous table. So going back to my virtual work calculation, now I can solve for FBC BC, and that is going to equal 39.33 divided by EA, which was what I had left out before. And so now we found the delta BC, we found the FBC, so we can go back to our compatibility equation, which you'll recall was delta BC plus FBC times the force in member BC equals 0. So we've solved for this one. It's 612.6 over EA. And we've solved for the flexibility, which is 39.33 divided by EA. And we want to solve this equation for FBC. So if we rearrange and solve, we get that FBC is negative 15.58 kilonewtons. And this is compression, because we assumed before that the redundant was applying a tension force to member BC. So when we made that cut, the unit loads that we applied put tension on the remaining parts of the member. So if I get a negative at the end of my analysis, then I know that that actual force is in compression. So now that we know one of the forces in the truss, we can go ahead and solve for all of the rest of the forces using only the equations of equilibrium. And we do that effectively by using the method of joints. So solve the full real truss. And it looks like this. So you'll recall we had external loads on our truss. These loads down here are the reactions, which we could always solve for right away since this truss system is externally statically determinate. But since it was internally statically indeterminate, then that meant that we had to use an internal redundant in order to find one of the forces within the truss before we could solve the rest of them. So we found that redundant, which was FBC, and we just solved to find that it's 15.58, and that's compression. So now, starting with this force, we can go ahead and calculate all the other ones. So I can start with the vertical equilibrium about point B to find this one. This is negative 99.49. I can do horizontal equilibrium at joint D to find this force, which is going to be 34.65 in compression. And then the horizontal equilibrium at B gives this force, which has to be in tension to resist the other ones. This is 55.5 tension. Vertical equilibrium at D gives us tension in member DC, or CD. It's negative 22.01 in compression. And then either vertical or horizontal equilibrium at joint C gives us negative 15.58, and that's in compression. And I can label all the compression ones negative to be consistent. This one is also compression. And so now I have solved all of the internal forces for this indeterminate truss using the force method with an internal redundant force, which was the force in member BC.